My name is George Vellidis. I'm the first speaker on the program today. The session is going to be primarily about irrigation and crop physiology associated with irrigation. My presentation is going to be about some new irrigation scheduling developments, things that producers will have available to them in a short period of time, but that aren't quite available yet. And if anybody's got a burning question while I'm going through this talk, please interrupt. There aren't very many of us in here, so people have an opportunity to have a good discussion. Again, my name is George Vellidis. I'm part of the Crop and Soil Science Department here at the University of Georgia's Tifton campus. And I'm going to talk to you about two types of irrigation scheduling projects that we've been doing. And both of them deal with technology mostly. The goal for both of these projects is to give producers and crop consultants some new tools that will help with irrigation scheduling, because as you all know, water resources are becoming an important issue in our state. So I'll begin with the first tool. And the first tool is a smartphone app for scheduling irrigation. And it's a project that's being conducted in collaboration with the University of Florida. And we're addressing with this project 4 different irrigation scheduling apps. There are apps for citrus, urban lawns, strawberries, and cotton, which is my responsibility of the project. The support for some of this work has come from Cotton Incorporated and the Georgia Cotton Commission over the years, and there's a lot of support from USDA and IFA as well. And we have, as you can see, a lot of collaborators. So the principle of all these apps is something that's not anything new. I think the innovation here is, for cotton specifically, is that we're developing this app for cotton, and then it's going to be converted to something you can use on a smartphone. That's the innovation. These principles that you see here are nothing new. We haven't come up with those. Those have been used for irrigation scheduling a long time. So anyway, just to run through them, we're going to be looking at how much water the soil can hold. That's sort of the primary thing that drives the app. So we keep a balance of how much water is in the soil, how much the plant is using, how much is added by rain, and how much is used by, how much is evaporated, and so on. We have to estimate the rooting depth of the crop as it grows. So that's something that's always something you have to estimate. We don't have hard and fast numbers for that. It depends on the soil type and so on. We're going to measure precipitation and irrigation, of course. That's a key part. Perhaps the most controversial part of these models and these types of schedules is that you have to estimate the evapotranspiration. And that is... I'll talk about this in a minute, but this is the most controversial part because you have to estimate how much water the plant is using and how much is being evaporated. And so that's not measurable, we're estimating that. So I'll move on to that. So the way that most people have approached this estimation is to use a theoretical estimation of evapotranspiration. You calculate that from environmental parameters. And the most accepted method is this thing called Penman-Monteith. It's the standard method accepted by the Food and Agricultural Organization. And then what you do is you have this estimated evapotranspiration. So this is a theoretical maximum, let's say, evapotranspiration, multiplied by a crop coefficient, which is how you convert this theoretical to what the crop is actually doing. And getting the right number for that crop coefficient is not an easy process. And you end up with the crop evapotranspiration, which you plug into the model. That's how you estimate how much water is being lost from the soil, either by the plant or by evaporation. So this app depends on weather data. Okay, that's how we calculate this ET. That's how we measure precipitation and so on. And because the app right now is being developed for Florida and Georgia, we're using the automated weather networks that are available in these states. In Georgia, we have 83 weather stations that UGA maintains all across the state. If you're not familiar with this, you can search for georgiaweather.net, and you can come up, it'll bring you this map, and you can click on any one of these dots, and you can find the weather conditions, current and past, for any one of those 83 spots in the state. Likewise for Florida, they have 79. So the app will be pulling data from these stations. So if you're, let's say, near Tifton and you want to use the app, you'll be pulling data from one of these 3 stations that are near us in Tifton County here. Okay, so here's a demo of one of the apps. This is not the cotton app. This is the strawberry app, or it might be the citrus app. These are the strawberry or the citrus apps which were already developed and just converted to smartphones. And so it's a demonstration floor. You see the picking the closest weather station or Alachua. You can also do it by going to a table instead of looking at the map, if that's easier. Then there's an information menu, which you have to go through once, where you set up the information for your fields. You tell it where your field is, the size of your field, the soil types, and so on. So that information is stored, and you don't have to enter it every time. More information about setting up your system. In some of these apps, for example, if you're using a drip system, the information about the drip system is important, so you have to put that information in here, the row spacing, and so on. And then here's what it gives you at the end. It gives you, how much water you have to apply and at what length of time from now. So 2 days from now, you have to apply 3/4 of an inch or an inch, and so on. And also it gives you access to the forecast so that you can make decisions about whether you want to wait. If the forecast is for precipitation, you can wait a day or so, put off irrigation, perhaps save an irrigation application that way. So I told you about the crop coefficient, and that being probably the most important thing that we can do to get this app to work right. And here's an example of the data we used this year when we ran the app. These are the different stages of the plant growth for cotton, and these are the different coefficients we used over time. These are averages put together from people who have done research on this topic across the Southeast. So they're not necessarily coefficients for Georgia. They were developed across the Southeast, from Mississippi all the way to South Carolina. I'm not going to bore you with this graph, but I do want to show you a couple of things in it. The main thing that's interesting is this is the zero line. So this would be when you run out of water in the soil, and this line here, whatever color it appears in this projector, it's hard for me to tell, is our model predicting how much water is available in the soil. So you see here, at some point, we're predicting that we're below zero, which means our model has over-predicted how much water the plant has used. Here we go up because we've had some rain and irrigation events, and here we go back down. I'm not worried about this part because we didn't start running our model until then. This was sort of back-calculated. But this part worries me because this is, when the crop's quite mature, and we really should be predicting that the plant has used more water than is available in the soil. So we have to work on that and fix it for this year when we're going to be testing it again. So here's some conclusions. The crop did fairly well, but we can't really take credit for that because we had a lot of rain this year. And so we have to make some adjustments to this KC, I think. And some of the adjustments we have to make is, here you notice we're going, so for our model, the user has to tell the model when the plant goes into these different stages. And we were waiting at this particular stage, so we had 80% of the field at first flower. We probably be back down to 50% of the field at first flower. And that way, this high KC is not running as long, using more water up. And then we probably have to adjust these a little bit. They may be a little bit too high. So those are the adjustments we're going to make this year and try it again. And we hope by the end of this growing season, upcoming growing season, we'll have a model that's ready for people to use. And we'll just have to find a way to distribute it so that if you have a smartphone, you can download this app and you can use it. We're going to try and use it with a few people this year on a test basis. Okay, so now I'm going to move on to the second project I want to describe to you. And this is a project that's taking place for the moment in the southwest part of the state. So those of you, I don't know if anybody's from that part of the state, but the lower Flint, you can see heavily irrigated, lots of pivots there. And the goal of this project, I'll get to that in a minute, it has a lot of partners you can see here. Very interesting partners, for example, unusual partners like the Niche Conservancy in this project. The Niche Conservancy is there to try and promote water conservation in the lower Flint because of the water war issues. So the project goals here are slightly different from the previous project. The previous one was to use soil, to estimate evapotranspiration. In this project, we're actually using soil moisture sensors to measure what's going on in the soil instead of estimating how much water the plants are using. And we're going to be using a bunch of technology to develop a scheduling tool that's at first targeted towards the lower Flint, but then eventually I think should be available to producers all over the state. And it's not just for cotton here, we're doing it for all the major crops in our rotation, corn, peanuts, and cotton. These are the technologies we've chosen to use. So these are all sort of high-tech solutions, but they're all true and tried. And people are using these quite a bit across the state and increasingly across the country. So we have variable rate irrigation. We have a suite of models that USDA has developed called Irrigator Pro, and these are irrigation scheduling tools that are very, very good. They work from using soil moisture sensors. So we have a soil moisture sensing system that UGA has developed that's part of this, that's an integral part of this, but it doesn't have to be the only soil moisture sensing system you can use. You can substitute this, the UGA one, for something else. And then we'll have internet-based delivery at first, and then eventually smartphone-based delivery for this project as well. A couple of slides to show you what the UGA soil moisture sensing system is. Some of you may be familiar with the watermarks that have been around in the market for at least 50 years. We found a way to sort of integrate them into a node, so we can put 3 of these sensors on the PVC stick and insert them in the ground in one hole. It makes it very easy to install and pull them out. And then we have some electronics over here. These wires connect to the electronics that allow us to communicate wirelessly back to a central location. And then we have a very nice antenna you can see here. We have a low-profile sensor that allows farm vehicles to drive right over our also moisture sensing system. So if you want to compare some commercially available systems like this one and this one, where they have a rigid presence in the field and you really can't drive over them, to the UGA one where you just have this flip antenna, you can just drive right over it. It's a nice system. And it's a lot cheaper than the others. It's not commercially available. That's the only detractor from the UGA system. So when we install the UGA soil moisture sensing system in the field, these yellow pins indicate where they were installed in this field during the summer of 2012. They set up a communication network, and they transmit their data back to the central location wirelessly. Okay, so you can have a lot of sensors out in this field, and they're communicating wirelessly back to the central location. And then from the central location, this is the central location here. It has a small network computer and a solar panel to charge the battery that feeds the computer. It's transmitted by a cellular modem to a web computer, a web server that's here on the Tifton campus. And I'll talk about what you see on the web server in just a minute. I wanted to show you a graph of what the data from the system looks like. And this is a sensor to measure soil water tension, which means it's measuring the energy the plants need to pull the water out of the soil. And on this particular graph, we're going from wet down here at 0 to dry up here at the top. And these 3 colors indicate the soil water tension in the soil at 3 different depths, at 4 inches, 12 inches, and 20 inches. And what's interesting, what I really wanted to show you was, you can see blue is the shallowest depth, yellow is the intermediate depth, and red is the deepest depth. You can see that with this, these little spikes at the top indicate irrigation precipitation events. You can see here there was a pretty big irrigation event, and it only wetted the top part of the profile. You see at 8 inches and 12 inches? 8 inches and, 12 inches and 20 inches, there was no effect of this irrigation. The water didn't get down that far. But this is the kind of information these soil moisture sensors give you. It shows you where your irrigations are going and how effective they are. Then later, when we had a big rain, it wetted the whole profile. So we have very valuable information coming from these sensors. Variable rate irrigation, I don't have time to describe all this to you, but I want to show you a picture of one of the fields down in Lower Flint. They're very complex. They have lots of features in them, so that you wouldn't want to irrigate anyway, so you can see what the VRI map does. So the VRI essentially allows you to turn off your sprinkler so you're not wetting the areas that you don't want to irrigate. You can change the rates that you apply in the rest of the field. And in this particular field, for example, just not wetting the areas that you don't want, so you save 30 acres in irrigation. This is a picture of the website where Irrigator Pro lives. It's the USDA models that I talked about. As I said, they're available for peanuts and corn and cotton, so these are an integral part of our scheduling. Excuse me. So when we collect the data from our soil moisture sensors, they go to the model, and then the model makes the decisions about whether to irrigate or not. And I just want to show you the last couple slides here, what we've got done so far this year. So this year we installed variable rate irrigation on 10 of these fields in the Lower Flint. There are 5 of them around Erie, 5 of them around Colquitt. And we installed our soil moisture sensing systems in all these fields. And I want you to compare 2 adjacent fields and see the response. Okay, remember, up is dry, down is wet. These are 2 adjacent fields, both in cotton. You can see this producer was managing this particular field so it stayed drier. This producer was managing this field so it stayed a lot wetter. And so with an irrigation scheduling tool, both producers perhaps can make better decisions about how to use their water and how to maximize their yield. And eventually, this is what we hope to have in a few weeks, The producer will be able to log into the web interface, be able to see what soil moisture sensors are doing throughout the field, and then get a irrigation recommendation for each one of these irrigation management zones from Irrigator Pro. You can see here one is recommended for 1 inch of rain and 1 inch of irrigation, and one for 3/4 of an inch, and the rest of the zones for no irrigation. So these are the things that we're going to be doing here in the short future, and these are what we're going to be doing as we get more research funds available to us. And that's the end of the presentation. Maybe we can take one question.
Mention your sheets.
Right, I'll mention that.
On your field-based units, is that using a radio signal back to talk to, and how will that be affected by cellular technology? Are you getting any interference? Have you lost any?
So we're using a low-power radio to communicate from one node to the other where the soil moisture sensors are. It works on 2 AA batteries. Those batteries last the whole season. The main thing that inhibits that signal is not cellular communications, but the canopy, and that's why we have our antenna coming up above the canopy, and that sort of takes care of the problem. We don't have any interference from other radio communications that we know of.
Back up about 3 or 4 slides. The one where it showed the different irrigation data.
Yes.
I know there's so many variables in each field, but it would be interesting to see time and yield from it. I know there are lots of other issues that impact, but it would be interesting to deliver the yield produced in those fields.
Yes, we hope that this year, when we actually start measuring some crop parameters, we actually are able to collect yield as well, so we will be able to quantify what's happening. You're right. It doesn't mean anything unless you look at the yield results. Okay, I think we've got to move on. I'll be here at the end of the session if you have questions. I want to remind you that if you wanted credits for attending the session, after you've listened to all 3 presentations, you can sign one of these forms and you get your credits.